this series of videos, we are going to expand upon our knowledge of Lewis structures by addressing the primary limitation of Lewis structures, which we can actually see by looking at the angles formed between the bonds of these three compounds. With carbon dioxide, if we look at the bonds formed between the two oxygens, these bonds both look like they are 180 degrees. Likewise, the bond formed between each of the hydrogens in boron trihydride look like 120 degrees. This appears to be the same pattern with CH4 methane, where the bonds formed between adjacent hydrogens are each 90 degrees. However, if you consider that these two hydrogens across from each other are technically also next to each other, this bond angle is 180 degrees. Now, why does CH4 have two different bond angles within it while the other two compounds do not? What you have just discovered is the primary limitation of Lewis structures, the fact that Lewis structures exist in 2D and cannot show 3D, but obviously molecules in real life exist in 3 dimensions. Therefore, we need a different visualization model in order to show what molecules look like in 3D. And the core foundation of that model is something that we call the valence shell electron pair repulsion theory, which we know primarily by its acronym VSEPR. The core of VSEPR is relatively simple. If you consider a pair of electrons or multiple pairs of electrons, these do not want to stay together because all electrons contain negative charge, which means that you are going to get repulsion force not just between the electrons within a pair, but between multiple electron pairs. For this reason, since each bond within a compound is made of a pair of electrons, these pairs of electrons will want to put as much distance between each other as possible, which is why in carbon dioxide, if we have two groups of bonds, two double bonds, the biggest angle we can make between those to make them as far away from each other as possible is 180 degrees, and likewise with boron trihydride, where we need to separate 3 bonding pairs, the biggest angle that we can make is 120 degrees. The core of this theory is that electron pairs will always try to maximize their distance away from each other. Now, the first question we need to answer in order to figure out a pattern behind valence shell electron pair repulsion theory is to figure out how many pairs of electrons each molecule has. And remember, a pair of electrons can either be a bonding pair or it can be a lone pair. In valence shell electron pair repulsion theory, groups that are made of bonds or lone pairs are what we call attachments for reasons that we'll get into later. Before we learn to construct molecules in 3D, we need to learn about something called AXE notation. So as attachments state, or based on the definition of attachments, electrons that are shown within a Lewis structure of a compound can either be a bond, where the two electrons are shared between two atoms, or they can be a lone pair, where the electrons belong only to a single atom. Now, if we break down what the letters AXE in AXE notation represents, each letter represents a different category or different part of the structure, where A represents the central atom of the structure. In this case, obviously, carbon is going to be our A. X represents what we call bonding groups, as opposed to individual bonds. We use the term bonding groups because when we talk about multiple bonds, which are double bonds or triple bonds, a double bond or a triple bond is only considered one bonding group, and we'll look at why when we take a look at the structure of CO2. E represents the total lone pairs within the structure. Now, it should be noted that X and E are specifically referring to the bonding groups and the lone pairs that belong specifically to the central atom, which is why A is present within this notation system. So when we count the number of bonding groups within CO2 and the number of lone pairs for AXE notation, we are referring specifically to anything that is attached to the central atom, carbon. In the case of carbon in CO2, it has 0 lone pairs. We don't count the lone pairs around oxygen because the oxygens are peripheral atoms and not the central atom. Now, we know that CO2, the carbon in CO2 has 4 bonds, but because they are double bonds and because multiple bonds only count as 1 bonding group each, carbon dioxide only has 2 bonding groups. Now, why is it 2 bonding groups and why not 4? Well, if we consider carbon dioxide, remember that each of the bonding groups is a double bond. Now, normally electrons will want to maximize the distance they are away from other electron pairs, but with double bonds or triple bonds, this maximization is not possible because the carbon and the oxygen are bonded together with these 2 double bonds. If we wanted to move one of the double bonds farther away, we would break the double bond and this would no longer be possible. So as a consequence, all of the electrons within multiple bonds that are within the same multiple bond need to be oriented in the same direction. And then these groups of electrons that form double bonds will then maximize the distance they are away from each other. And since each of these pairs of electrons in each of the bonds of the double bonds are considered part of the same bonding group, one bonding group will position itself as far away from the other bonding group as possible. Now, if we combine this into carbon dioxide's AXE notation, we call this an AX2E0 compound. Again, A meaning that the central atom carbon has 2 bonding groups attached to it and 0 lone pairs that are attached to the central atom. If you want to simplify this and simply write AX2, this is also correct. Finally, if we take a look at the structure of NH3 to see an example of an AXE notation that actually has a lone pair, let's consider NH3. We know that the central atom of NH3 is nitrogen, so we're going to ignore any lone pairs or bonds that are not attached to nitrogen. We know that the nitrogen has 3 bonds, single bonds all connecting the 3 hydrogens, so its X would be 3. And the number of lone pairs that are attached to nitrogen is 1, which means that NH3's AXE notation is A, again representing nitrogen, X3, the fact that there are 3 bonds attached to the central atom, E1, indicating that there is 1 lone pair that is attached to the central atom. If you simply want to write this as AX3E, it is implied if there's no number below the E that the number is 1, and both of these are equally correct. In the next video, we're going to take a look at how AXE notation can be used in order to represent molecular structures in 3D, and for now, to make sure that you have a solid understanding of AXE notations, you can try the practice problems below, in which you will need to practice and solidify your understanding of drawing Lewis structures in 2D, and then using that structure to identify the number of lone pairs and bonding groups in order to find the AXE notation of the structure.